It always seems like a big mystery how nature, seemingly so effortlessly, manages to produce so much that seems to us so complex. Well, I think we've found its secret. It's just sampling what's out there in the computational universe.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind.
Your hosts here in North Devon, Matthew and George Russell.
Oh yeah, baby, Stephen Wolfram. Yeah, so again, George joins me. Hi, George.
Hi.
Hi, good old George, the voice of the early podcasts. Yes, George, you wanted to come on because you wanted to talk about cellular automata. Is that right?
Yeah, that is right. Yeah. Or automata. How is it pronounced?
Yeah, I don't know. Automata. Yes, I think that's probably better. Now, obviously, I don't think there's going to be many space podcasts this week that are going to be talking about this.
Yeah, probably only 2 or something.
Maybe 2 out of the 6,722 space podcasts currently available on Spotify and other
streaming
platforms.
platforms.
Yeah. George.
Yeah.
Before we go into that, I want to talk about going to the moon to look at water.
Nice.
Right, because I saw a little interesting story about a slight kind of worry about an up-and-coming mission. Do you want to hear about it?
What is the worry?
Well, the worry is that that they should perhaps fly another mission before it. But we'll get on to that. It's interesting. So just a recap of the roadmap that gets us there. So have you heard of the International Space Exploration Coordination Group?
No.
It's the ISECG, a classic initialization. So it's 14 space agencies. Now, I can't name 14 space agencies, but I'm pretty certain they're out there.
Yeah.
We've got
well,
NASA, ESA, UK Space Agency, JAXA, ISRO, the Australians, the Canadians.
The Chinese.
Ooh, I wonder if the Chinese are involved. Anyway, they've developed a global exploration roadmap, or a GER, that provides a framework for coordinated efforts regarding robotic and human space exploration. Right?
Nice.
So the whole aim of this global exploration roadmap, or the GER, is to expand human presence into the solar system and to understand our place in the universe. So that's pretty, heady goals. So yes, at the moment, the GER is starting its space exploration program with the existing International Space Station, or the ISS. And then that goes to the lunar vicinity, then to the lunar surface, and then to Mars. So obviously that's like which program that NASA have at the moment?
The Artemis.
Yeah, that's right, Artemis. Yeah, the logo of the Artemis is very much got all of those elements in it. So yes, the recent version of the GER focuses on lunar vicinity and lunar surface, introducing the Deep Space Gateway, or the DSG, facility developed in lunar orbit for astronauts. So they can basically, the whole idea of the DSG, the Deep Space Gateway, is that astronauts can be on the gateway and access different parts of the moon that aren't necessarily accessible by just directly going there, like we did with Apollo.
Right.
Particularly things like the South Pole.
So would this be in orbit, or?
Yeah, so it's like the International Space Station, except
but for the moon.
A rubbishy version that goes around the moon,
and
a load more dangerous.
So it'll be able to adjust its orbit so that landing on different parts of the moon are more easy.
Yeah. So it's in a massive sort of
polar orbit.
Yeah, it's in a polar orbit, but it's very eccentric as well, the orbit that it has. So it goes very close and very far out. So there's different kind of.
So it has the highest range of.
Yeah, so it's got good range. So as part of that Artemis program, you've got the gateway, and hopefully, astronauts will be going to the lunar surface in 2024. But I find that very hard to believe. It's going to slip. 2024 is a bit early. Yeah, there's no way.
Especially with all the COVID and
Yeah, well, COVID set it back, but I think it was always ambitious. But I think it's, the ambition has at least sped it up. Maybe we will see 2026.
Yeah.
That's not too bad.
They said the Wright brothers would happen in 1 million years, and it happened the week after that article in the newspaper was posted. So,
wow. Okay. That's definitely an error.
To be fair, the reasoning was pretty terrible, saying that, like birds took millions of years to evolve flight, so I suppose it's the same with humans, right?
Yeah, that's awful reasoning. Yeah, because one relied on the glacial natural selection, and the other, while as the Wright brothers relied on computational skill and science.
Yeah.
Yeah. Right. So one of the early things that they want to do as part of this GER, Global Exploration Roadmap, is to go to the South Pole region and look at polar volatiles.
What is a polar volatile?
It's not a polar bear, an angry polar bear. But that would be. But although that is a polar volatile, no, it's water basically. So is there water at the polar ice caps of the moon? And can you get your hands on it? And if you can, it's really, really interesting. Why?
Because that means life, right?
Well, it means what?
Life.
Life. We're not going to see life on the moon. I don't think they're interested in it because of that.
Well, it's got water on it. Surely that.
Well,
has
yeah,
something.
I suppose there's a chance. But what's more interesting about ice that's found at the moon's south pole?
You can make fuel out of water.
You can make fuel out of water. That's though you get the gas station, which helps humans expand into the solar system. That's one. Actually, I think probably the more exciting is because this is like a part of the solar system. The craters on the moon may have ice there that's existed for billions of years that you can then do experiments on and actually have some real insight into the early solar system.
Nice.
Yeah. So it's scientifically very, very important, but it's also very important as part of the GER, which is what stands for what?
There's too many of them.
The Global Exploration Roadmap.
Oh, of course.
Yeah, the GER.
Or the GERs, I like to say.
I like the GER. There's many GERs, or Germany. Sounds a bit like Germany. Right.
It actually is Germany. If you just
yes, it is Germany.
The letters,
yes, it is the letters. But so one of the things they're going to send, one of the things that's really important as part of Artemis, is Viper. Now, we have mentioned this before on the show. Viper is the Volatiles Investigating Polar Exploration Rover.
A rover exploring polar volatiles.
So yes, in the next, soon, hopefully in 2023, November 2023. So only a couple of years away now, we will see a rover. It's quite a big little thing. It's like a golf cart, that sort of size, like
similar to Curiosity and all of those.
It's probably. I don't think it's as heavy as that because it's only 430 kilograms. I think Curiosity and is quite a bit bigger than that. So those, but it's 8 feet tall. This thing. It's pretty cool, isn't it? And about 1.5 meters in length. So it's a big thing. And they guess how much it's going to cost to run this thing for NASA.
Is it something like, and I'll take a wild guess here, $433.5 million?
That's a very good guess. It's only absolutely spot on. But you can't. But actually, that's not the only cost, because NASA also had to give Astrobotic Technology in Pittsburgh. They had to give them another almost $200 million to develop the sort of landing systems, the actual spacecraft that carries the Viper to the moon and lands it on the moon. So, it's not going to be easy, that. So Astrobotic have got that contract to do that. Do you know what it launches on in 2023?
Ariane 6.
Oh, if only. No, not an Ariane 6. I don't think an Ariane 6 would be powerful enough, actually.
A recommissioned Saturn V?
A recommissioned Saturn V is exactly the wrong answer. What's a really powerful rocket that's in use today?
Falcon Heavy.
Falcon Heavy. Falcon Heavy goes up on a Falcon Heavy. Yeah. Now, I thought what was interesting is that the project manager on this is Daniel Andrews, but the project scientist is this really cool guy called Anthony Colapreet. Now, he's really quite recognised for his work on Martian climate. He's like a bang-out scientist, basically.
He's a really good weather reporter for Mars.
He's a very good weather reporter for Mars. But he's also part of this NASA Ames lunar robotic program. Very, very influential on science. Or AMES. But it's Ames. It's not also. So,
it is if you pronounce it wrong.
Yeah. So Viper, yes, is this rover, and it's part of the Lunar Discovery and Exploration Program managed by the Science Mission Directorate at NASA headquarters. And it's there to support the Artemis program. So it's going there to sort of prospect for ice before human exploration goes there, which is one of the problems that's going to come up, you'll see. But Viper, do you know what a Viper is?
A small kind of like medium-sized snake?
Yeah. And in this country, we have the common viper, but in this country, we also call them adders. Did you know that?
I didn't know vipers and adders were the same thing.
Yeah, in this country they are. I don't think a viper that you find in America, I think, is different. But a common viper and a common adder in this country, the same thing. Hence the joke, why did the viper nose? Because the adder handkerchief. What do you think?
It's pretty good.
Yeah, it's what my dad used to say all the time.
And adder's the only venomous snake in Britain.
Yeah. So there's a lot of sort of folklore around the adder in this country. So it would have been cool if they'd come up with another acronym that was adder instead of viper. But anyway, we've definitely got digressed there. So yes, there was a NASA rover concept for going to the moon, which has a more obvious name called Resource Prospector. But that was cancelled in 2018 and became this Viper project. So the Astrobotics Griffin lander is the thing that's going to take it to the moon, and that's part of the Commercial Lunar Payload Services Initiative, or CLIPS, which is things like Blue Origin's Blue Moon is another CLIPS type thing.
Is that the same, or is it just an alternative?
No, it's
part of the
no. There's
group.
lots of missions that are going to be part of this Commercial Lunar Payload Services Initiative. So there's lots of. They're going to be sending lots of different fleets of robotic craft to the moon to prospect and to prepare for human landing.
So is this lander owned by the CLIPS company?
No. CLIPS is like a NASA initiative.
Oh, it's like a section.
Yeah.
Of
It's
NASA.
it's like a sort of. They came up with a little program called CLIPS. And then they've been awarding money to various companies like Blue Origin and SpaceX.
Can make a commercial lander.
Can make commercial stuff for Artemis.
Right.
Whereas NASA are going to concentrate on SLS and things like that.
So basically, they just want to set up a commercial lander for the moon.
And this is one of them. And this will be quite a big one. Now, the Viper is going to land at the western edge of Nobile Crater, which is on the moon's south pole. And it's going to try and travel like 25 kilometers over its 100-day mission, drilling into ice, mapping the ice, looking at various places of light and dark and shade, etc., etc. And the reason why NASA chose Nobile Crater, and Nobile is apparently an Italian explorer who helped design Arctic exploration airships, which is pretty cool, isn't it?
That's cool.
So Nobile is probably how you pronounce it. I don't know, but Nobile Crater, it's got lots of different sort of variety of locations there. So that's one of the reasons why they're interested in it. It's actually easy for Viper to sort of travel across that terrain. So they chose it because of that. They chose it because there's just enough sunlight for the rover to keep charging up its batteries using solar panels. And there's a good line of sight between the crater and Earth, which is important because what?
Because if you lose communication, you've got to... Well, also, you just got to have communication in the first place, right?
Yeah. But I mean, I suppose you could do the communication via the
orbital
the
relay.
Deep Space Gateway,
that doesn't,
or do like the Chinese did and actually send a specific satellite or CubeSat out that way to do the relay.
Well, any Martian lander has it a subsequent,
relay
orbiter,
point.
relay orbiter.
Yeah. Which is one of the problems, of course, because if suddenly some of those pack up, then there's no way of talking to Curiosity.
Well, I guess you just send another duplicate, right? And then it's slightly
cheaper
cheaper than
just send another.
Well,
it's pretty difficult
it's
to
cheaper than,
just send another.
It's cheaper than just like
Giving
completely
up.
redoing.
Yeah. No, absolutely. But what I'm saying is, there's a danger of
like
a couple of satellite failures, and then suddenly we might lose contact with all the rovers on Mars, which would be a downer because it's very expensive to get to Mars.
And to run the whole thing.
And remember, the launch windows only open once every
4 years.
2 years.
2 years.
2 years, a couple of years. And sometimes they get harder as well. So it's going to enter permanently shadowed locations, and it has to run on battery power and then be able to drive to a sunlit area to charge up. So that's got to be risky, right? So there's risky maneuvers that it has to do.
But that's just space for you.
Yeah. And it's got a bunch of instruments and a big drill. So this drill is made by this company called Honeybee Robotics, and it can drill about 1 meter down. And then it's got 3 different spectrometers that look at the samples and see, read all the information about whether it's water and et cetera, et cetera. So it's out there now. All the data that about Nobile Crater actually comes from several missions. So you'll have heard of some of these. There's Luna 24, there's Lunar Reconnaissance Orbiter, or the LRO, which is quite famous because it took pictures of the Apollo landing sites and things. There's the Chandrayaan 1 and the Lunar Crater Observation and Sensing Satellite. So those missions have kind of shown that there is actually water on the moon, which was actually quite a surprise, I think. Even though it's, very thinly dotted across the Martian surface, it's there. And the whole idea is that maybe there's big chunks of water in these permanently shadowed craters, particularly in the South Pole region.
Right.
So
how many of these perfectly shadowed craters are there?
I don't know. There's quite a few.
Like as like a percentage of the moon's surface,
probably. Tiny
Tiny
percentage of the moon's surface. But it means that there's probably a lot of ice there. And when I say a lot, there was some industry and governmental panel of experts that reckon in the near term they could use 450 metric tons of lunar-derived propellant. So that's 2,450 metric tons of processed lunar water, which would generate a new economy of $2.4 billion US.
And who would be buying the propellant then?
Well, I guess people wanting to then go on to explore the rest of the solar system.
But you got to hope that people are there to buy it.
Yeah, I mean, buy it or just use it as a resource that saves you money from dragging water up into, what you don't want to do is drag rocket fuel from the surface of the Earth up the massive gravity well.
Yeah.
When you can mine it on the moon and save loads of money doing it that way.
Yeah, I mean, obviously having the ability to mine your fuel on the way to a trip saves you a lot of delta V.
No, absolutely. But even though this Viper mission is absolutely, it's got the green light, absolutely everything is happening for this mission, there are a couple of scientists who are a little bit worried that they perhaps could do something more. So Bethany Ehlmann, who's a planetary scientist at Caltech, she actually says, it's not like water ice is everywhere. The detail matters in terms of where we go. Remember, this rover is only going to drive 24 kilometers. And I know the moon looks small, but it's absolutely enormous, right? So we can't, you don't want to make a mistake and then find nothing. But then, Anthony Colaprete, this Martian weatherman, he counters that and says that's exactly why we're going. The whole point is that any new information is going to be enlightening, whether they find something or not.
Yeah.
That's one of the reasons why they're going. But there's another scientist, Clive Neal, who's a geoscientist at Notre Dame in Indiana, the University of Notre Dame in Indiana. He says that that Viper may not even come across water. Let me just make sure that I've got a good quote from him. So he's worried that there's this other. What he's basically saying, and I think what Bethany Ehrman is saying as well, is that there's another mission called Lunar Trailblazer, which is basically a satellite that's there, is a little small spacecraft that's there to prospect for water, and it will actually do a sort of really good job at showing where the rover should go, right? And Neil and Elman are both thinking that it's a real missed opportunity that Trailblazer isn't launched at the same time or before Viper, right? So there's a little bit of a kind of, a little bit of a bit of a ruckus, a little bit of a disagreement there. But NASA are absolutely adamant that they're going to store Trailblazer until 2025, when it's scheduled to ride along with another unrelated spacecraft. So this is, it's a completely different.
Do we know what spacecraft that is yet, or are they just
No,
leaving an empty seat in case?
I don't know. There's probably another spacecraft that's being launched at the same time, like an Earth observation satellite or something like that. So it'll be one of those ones where a couple are riding up on the same.
Yeah, it often happens with CubeSats and things. They just shove them in the extra space.
Yeah. But this one isn't one. I mean, it's like Ariane 5, for example, pretty much always has two satellites, a primary and a secondary load of two large satellites, basically.
Yeah.
And I guess it's something similar is happening here. They must have booked the ride into space or something. But NASA are reluctant, even though Bethany Ehrman, who is the principal investigator for Lunar Trailblazer, says that the launch actually will be ready in February 2023, so way before Viper. So they could launch it. But at the end of the day, Laurie Glaze, who's the director of NASA's Planetary Science Division, basically says we absolutely have sufficient knowledge to fly the Viper mission before Trailblazer. So NASA have gone with, let's just go with Viper. Let's not worry about Trailblazer. We can use Trailblazer later on to get more information. And so, that's kind of how it's ended up. What do you think?
I think
it just seemed like, I don't understand why you would have a satellite, you'd have a spacecraft built and then keep it in storage when it could be useful for another mission.
Yeah, it seems like the longer you have it on the moon, the better.
Yeah, exactly.
But I guess you get the boosted efficiency of putting it on the same spacecraft. And
I think there must be something like the operations of these things are very, very hard to kind of put together. There's the logistics of getting them into space in the first place, all those sort of things. So I guess NASA have looked into all of that and basically are saying, look, Viper's got a good chance of finding ice, so let's not worry about it. It'd be pretty annoying if they don't, though, right?
Yeah, but like with there was a mission recently with Mars that crashed, the Easter mission to Mars. Mm-hmm. They said still that it was like a 95% success because they had done so much even if you don't achieve the main objective, you're still, getting so much information out of any mission.
Well, that was the Schiaparelli, wasn't it?
Yeah.
But which, did a pretty good job, but it just added to that whole thing that no one ever had successfully landed on Mars except the Americans.
It's a sad reality.
But Chinese have done it now since then. So well done, China. China did it on their first attempt. That's how bang out they are. Right. I thought we'd also talk about Lucy. Lucy was something that we covered way back in January 2017 when you were still the voice of the podcast.
Wow, that's way back.
That is way back. We're talking vintage space there. vintage Interplanetary. And we mentioned it because that was the week, January 2017, where Lucy and another mission called Psyche were announced as part of the Discovery class missions. So I think they were 13 and 14 or 14 and 15 Discovery class missions, something like that. And yeah, so this Lucy spacecraft has been built. So like NASA announced that Lucy would launch in October 2021, way back in 2019. And guess what? Next week, it's October 2021. So guess what's likely to be launching next week?
None other than Lucy.
Yeah, none other than Lucy on an Atlas V401 from Cape Canaveral. SpaceX were pretty annoyed by that, by the way, because they didn't get a chance to... well, I think they did. They just basically said that they could do it loads cheaper. But NASA just insisted on using the Atlas. So that was that. And SpaceX dropped their protest. But even that was a little bit controversial. So, so Lucy has passed all its tests. It's got green light. So if you were listening to my podcast a couple of weeks ago about how those missions progress through their various phases, A, B, C, and D, it's got through all of those key decision points, or KDPs. It's got through all those milestones. And yeah, so it's, it was delivered in October last year. And then the spacecraft headed to Florida back in August. And the launch window for Lucy opens on the 16th of October. So NASA are going to have a virtual meeting this Tuesday, September the 28th, and go over the whole mission, which is basically the Trojan asteroids that follow and trail Jupiter in its orbit around the sun. So this is all about Lagrange points. So where there's Lagrange points with Jupiter, there's all these weird Trojan asteroids that are essentially sort of stuck.
It's kind of like those places in the sea where like trash kind of piles up.
Yeah, it is,
because there's no current.
Yeah, it's a little bit like that because it's where the currents are kind of balanced up.
But being pulled either side.
Yeah, but so these are kind of gravitational currents at L4 and L5 of Jupiter. Now the ones at L4 are known as Greek camp Trojans.
Why are they called Greek camp Trojans?
I guess it's because I think they're sort of seen like armies that are camped out, and so you've got the Greek camp and the Trojan camp either side of Jupiter, and they're these little asteroids that are going around. So you've got, you've got L4 and L5.
Well,
L4 is the
Greek camps. Oh yeah,
and the Trojan camp are at L5. Yeah, but they're all Trojans, which is a bit confusing.
Why so many missions toward Greek camp?
I don't know. Actually, that's a really interesting point. So. First of all, though, you've got it's a 12-year mission. This is going to take a long time to do. So, by the time they get to some of these, it's going to be.
And that's more than Apollo, right? So.
Oh God, yeah, but it's this is common for things like
these deep space missions.
To take a long time.
Past the rocky planets.
Past the rocky planets. It's going to take a long time.
Measuring years.
Yeah. So Lucy's going to go to a record number of asteroids that are in separate orbits around the sun. So one of them is the first one it's going to visit. Actually, is a main belt asteroid that's obviously located in between Mars and Jupiter, and that's called the Donald Johanson 52246 Donald Johanson asteroid, which is about only 4 kilometers in diameter, I believe. C-type asteroid.
How much gravity would you get out of these 64 kilometer?
I don't know how much you get. Well, you could work it out. It's a very tiny percentage of what you have on Earth, but it's enough to orbit round, presumably.
Yeah, just really slowly.
Yeah. So the 20th of April 2025 is the first time that Lucy will fly past an asteroid and do some measurements, and it will fly by at about 900 kilometers away. So quite close. Then 2 years later, Lucy will get to the Greek camp. And this one's a big old 64-kilometer satellite. And it's the largest member of the Trojans. And it itself has a small satellite.
It's moons within moons.
It's moons within moons within moons. So yes, so that'll be interesting. I mean, that'll be really cool anyway.
Yeah, because I suppose at these Lagrange points, since there's no other interference, even the smallest objects can have moons.
Yeah. Well, yeah, it's an interesting.
Even a person could have a moon.
Yeah, you could have a little moon around a person. Yeah, I wonder if they ever worry about Lucy herself as she flies in, disrupting that delicate balance.
I suppose she, compared to a 4-kilometer diameter rock, has little impact on the gravity.
This little Keter satellite, as it's called, that orbits Eurybates, is a kilometer. It's a kilometer wide, so it's big, I suppose. Yeah, it's much heavier than Lucy. And then after visiting it will very quickly, a month later, go and visit another asteroid, Polymele, and which is only 21 kilometers. Then 6 months later, go to another Greek camp asteroid. Have a look at that. Swing by a few months later to another Greek camp one, which is massive, 51 kilometers. And then, really cool, it will swing over and take about 5 years, which I think it has to come back round to Earth to do a gravity assist. Now, this is the interesting thing. No other spacecraft has gone out to the outer solar system, to the gas giants, and then come back again. So, yeah, Lucy's got to come all the way back to a couple
and not even to come back, just to swing round,
just
to get
do a gravity assist,
boost of just to come back to the same place. That's insane.
To go the other side of Jupiter.
Yeah,
that's the orbital mechanics that's required here. So it's really interesting. So it's going to take 5 years, and then it'll go over to the Trojan camp at L5 to have a look at Patroclus, which is 113 kilometer Trojan, which is massive, and that's got a satellite, which presumably is a bit of a binary because that's 104 kilometers.
Yeah, I suppose they just say whatever's the lightest is.
Yeah. So the pair orbit at a separation of 680 kilometers. So there's this spinning binary of two very large objects.
And the speed of these orbits are like insanely slow, right?
Yeah, I would have thought so. Yeah, and so you've got this. Yeah, these. I mean, that's going to be really interesting, isn't it? So it's an ace mission, Lucy. I really like it. I think I prefer Psyche as a mission because the whole idea of an asteroid that's a great big lump of metal and potentially the core of an old planet is really cool.
Like the prospect of asteroid mining generally is quite cool.
Yeah.
I mean, it is the future of resources.
Well, it may be the future of resources. It does seem that way.
Yeah, I mean, we'll run out of stuff on Earth eventually.
Yeah.
We use it at exponential rates. And
yeah. And I guess missions like Lucy and Psyche will go down as very useful missions in terms of having a look at what these things are like.
Yeah, I suppose just as much as, the original voyages to America helped in the gold mining and things.
Yeah, absolutely. So that's going to be flying. That's one launch that I'm really, really looking forward to. And the launch window, like I said, opens in a couple of weeks. And there's a NASA press conference coming up this week about that mission. So that is super, super cool mission. Very, very cool indeed. Right, what you wanted to talk about is cellular automata.
Yeah.
Automata. Yes, well, we started off with a quote from this guy called Stephen Wolfram.
Yeah, creator of Wolfram Alpha, Mathematica.
Yeah, so Wolfram Alpha I've got on my phone. I use it to do things like, you can put in things like, what's the diameter of the moon? And it will tell you very accurately.
Yeah, or you can say like diameter of the moon divided by the economy of Kenya, and it will give you some results there as well.
It's really good. I have to say, it's a very useful little thing, particularly for finding out definite facts about space. It's very good. So that's one thing. I didn't realize he's a Brit. I've always thought that Wolfram was an American for some reason, but he's an utter Brit. And I still can't get over this. He was 14 and he'd already written 3 books on particle physics. So at 14, he went to Oxford when he was 17, but he left because he went to Caltech, another person from Caltech. He went to Caltech to get his PhD by the time he was 20. And his PhD advisor was none other than Richard Feynman. How cool is that?
It's pretty cool.
Yes. And he's also he's the youngest recipient of the MacArthur Fellowship at Caltech at the age of 21. But a little space fact: Wolfram helped develop that kind of weird. He was the consultant with that weird language that's in the film Arrival.
Yeah. He helped design it alongside his son, or like
his son and him sort of did a lot of the visualizations for it. Yeah. That it's based on the Wolfram language. So Wolfram, but he started off as doing sort of particle physics, but he became obsessed with cellular automata or cellular automata. Now, cellular automata kind of actually started life
with the game of life.
No, way before that. In fact, 2 like absolute geniuses at Los Alamos. Which come up quite a lot, these 2 in space when you're talking about space, is Stanislav Ulam and von Neumann. Obviously, von Neumann comes up loads.
Yeah, which the von Neumann probe is named after.
Yeah, and Stanislav Ulam comes up loads as well when you're talking about orbital mechanics and things. So, these 2 came up with this original concept of cellular automata. Now, go on. You give us a kind of layman's version of what these things are.
If you want to get started with like cellular automata and stuff, the one you look at is Game of Life, right? John Conway, who's also a Brit as well, a mathematician. And it's essentially a cellular automata, which means there is a grid of cells, right? And each cell or square,
like square paper. You could
like a chessboard, like a Go board or a shogi board or something,
yeah.
chessboard, something like that. And then each square or cell is either on or off, right? Either black or white. And the way each cell has neighbors, so I have 8 neighbors. The 4 orthogonal directions and the 4 diagonal directions. You can think of this like the king moves in chess. And depending on the number of on cells or off cells in its neighboring cells will determine whether or not it'll be on or off in the next generation. Yeah. So, for example, if you had the rules for the Game of Life, for example, are if there are 2 or less cells, neighboring cells which are turned on, then it will die. Or sorry, less than 2 cells, then it will die. If it has equal to 3 cells, and it's a cell which is off, then it will be born. So if an off cell has 3 alive cells, then it will be born. And if it has 4 or more neighboring cells, then it will die as if by overpopulation. So you have these very simple rules, and what you'd expect from a system like this, where you have a simple initial condition, whatever it might be, and simple like layout to how things work and the simple rules, you'd expect that this would lead to very simple behavior and very simple patterns. But actually, not only is it incredibly complex, it's indecidably complex. It's you can't predict. There's no reducibility at all. It's completely computationally irreducible. And it's been proven within Conway's Game of Life. You can create universal Turing machines within it, right? So you could run, and in fact, people have actually done this. Run Game of Life in Game of Life. If you set up these cells and turn the right ones on and the right ones off, and in a certain pattern, it will produce. You can create computers which can run Windows. Like all you need is just these amount of cells.
Well, so they're known as Turing complete. Is that right?
Yeah. Turing. If something's Turing complete, it means it can run itself.
Yeah, and so the Game of Life, that was kind of cellular automata made popular, wasn't it? So since like the 1940s, von Neumann version. No, it was just a mathematical curiosity, and then Conway made it popular in the 70s with Game of Life, and then Wolfram seems to have become obsessed with it in the 80s.
Well, there's another Cellular Automata which is really important and influential as well, which give rise to something like Rule 30, for example, which is
these are the Wolfram.
The Wolfram Cellular Automata, where you start with a square, which you again have a grid of squares, except this time it's not 2D, it's actually 1D.
Yeah.
Or kind of like 1D with
You're
one time.
just moving down the
down the time dimension. So it's sort of a one-dimensional time with time.
Yeah.
And essentially you start with you have these rules where you say, depending on what's above a square, the three above it, so you can think of that as the neighbors.
Yeah.
It will determine its state.
Yeah.
So you could have a rule that was like, if it has one, like the middle one above it is turned on, and the two next to that is turned off, then it will turn on.
Yeah.
And if you ran that on just one cell turned on, you get a line that went straight down.
Yeah.
But again, you would expect something so simple with these simple rules to produce incredibly simple things, the things you could find patterns eventually. But again, that's wrong. In fact, Rule 30 is the most famous, and it's Stephen's favourite cellular automata, or just generally
one of his favourites. It's in his top 4.
It's got to be in at least the top 4. But no, that gives rise not only to complexity, but again, even after many decades of many people trying to find patterns in it, it's still, there's nothing. Like, there's no repeats.
Yeah, that central line never repeats, does it? It's a bit like pi.
Yeah, it's so random, in fact, or at least seemingly random.
Well, he uses it as a random number generator.
It's used as a random number generator in many programs.
Yeah. But even though some people object to that because other columns aren't random, that's the weird thing with it, isn't it?
Yeah. The left side of Rule 30 is actually a repeating pattern.
Yeah.
You can very easily see its repeats, and yet the middles and
the right hand side is like completely crazy. But what I love about the patterns that are drawn, so they all look like triangles because it's kind of one dot and it sort of spreads out.
But it collides with others on the side,
and so what's awesome about it is that some of them, he puts them into different categories, doesn't they? Because some of them are simple, some of them die.
Yeah, I mean,
some of them are a pattern that you can clearly see a pattern forming, and then some of them, like Rule 30, are completely diverse. And just like Conway's Game of Life, you can create Turing machines. And in fact, this Matthew Cook should get a shout out here because he's one of his research assistants actually did a proof that indeed it was a Turing complete process. This Rule 30.
Also, we should mention Gosper as well, creator of the Gosper gun, Gosper glider gun, which in Game of Life is a setup of cells that can shoot in some ways these gliders. So it's essentially creating an infinite array of these systems which can move across the board. Yeah.
I mean, the Game of Life thing's really incredible. And I guess what's brilliant about this is that it's a really good demonstration. And I was, trying to apply this to life and physics and space. But I really liked the one that I read about this whole idea of, say you look at something like a bee, and like a bunch of bees get together and they can make a beehive, right?
Yeah.
And it's like they've only got a simple set of rules, but because of one particular set of rules, for some reason, you get this vast complexity of a beehive.
Yeah, I mean, there's no blueprint.
There's no blueprint for the beehive.
There's no blueprint for a beehive in a bee's mind because there's just not enough space for that.
Yeah, exactly. And the bee itself has no idea.
Doesn't know what a beehive is.
No, it doesn't know what a beehive is. And therefore, the complexity of the beehive is just an emergent property of a very simple set of rules. In the same way that these cellular automata, you get this emergent property of a totally random number sequence down the middle line.
Except it isn't random. That's the crazy thing, is that it just appears random, but it is deterministic. You know exactly why each cell is the way it is. but you only know after you've computed it. That's the thing.
Yeah,
So there's no repeats.
So that's why it's computationally irreducible.
Irreducible because
You have to run it to find it.
Yeah.
But then to find it, you know that it is it.
yeah,
But you have to run it first.
yeah, exactly. It's not like if you were to have a pattern that was like 1 3 1 3 1 3. Well, I know I can create a formula that you'd input like what number in that sequence you'll have, and then it will output the what number it will be, because that's a very simple pattern. But for some reason, these cellular automata are producing patterns that are just exactly irreducibly complex.
Yeah, but what's really cool is this Rule 30, for example, you can really see its kind of random nature and what it looks like. But it looks like things like snail shells have got this Rule 30 actually drawn onto them.
There is a snail that has something like Rule 30 on its shell, like just drawn on.
Which is well, which just goes to show that this complexity is coming from this very simple set of rules. And
Scientists think that each individual cell is, reading the cells adjacent to it in a similar way.
So Wolfram, I think, is going down this kind of path where he believes that maybe the rules of the universe itself, like why are there fundamental particles, why do we see complexity around us, why do we see galaxies and stuff like that, is again caused by like something like cellular automata, and maybe you could actually describe the universe with a simple set of rules. Am I right in saying that?
Well, yeah, exactly. That he has a model of. We all hear about these like universal models of physics, that can combine all of these various things. But I think my favorite is this Wolfram model of physics, where he has designed a cellular automata, which he calls the most structureless structure. In other words, the most abstract form of these. So it's dimensionless. Has a time dimension, but again, that's similar with all of these cellular automata. It's just the iterating of, the rewriting of the state based on rules. And essentially the way it works is it's a graph or hypergraph. So just a list of, I guess, vertices that each are unique in the sense that they're numbered or lettered or labeled in any way. It's completely arbitrary, the numbering. Mm-hmm. But essentially, let's say you had a vertice 1 and 2 and 3, right? So you had 3 vertices, and you were to join them by a hyperedge. And hyperedge is just an edge which joins more than 2 vertices. So a normal edge will join 2 vertices. Hyperedges join 3 or more.
So a ruler, for example, isn't a hyper edge.
It's not a hyper edge.
But one of those bendy rulers you could. That sort of thing, like a piece of string.
Probably more like a rubber band or something. You can wrap around 3 pins.
Oh, yeah. Yeah, okay. Okay, that's a good one. Yeah.
But no. So and then the way you'd notate a state in this cellular automata is you just literally write, you bracket, well, the way it's notated is you write brackets, and then inside those brackets, you write the 3 or more vertices, which is hyperedge is connected to. So in this case, I said it was 1, 2, 3, and they're all connected. Then you have a hyperedge, which is 1, 2, 3. Right? And the ordering of those numbers doesn't matter. It's just an edge which connects 3 things. Mm-hmm. But with this very simple setup, just like with the game of life, you can actually get some pretty crazy things from it. So the way the rules work is actually, unlike with the game of life, it's only one rule. But similar to the game of life, what it does is it says, find this thing where this thing is true, and then if it is, replace it with this thing. Yeah. So if you had a system that was like, if you had three hyperedges, for example, that were all connected to one vertice. So it's like a vertice is connected to itself 3 times. And to make things simple, we'll just make it normal edges, right? So if a vertice is called 1, then we'll say that there are 3 hyperedges, and each hyperedge is 1, 1, right? It's connected to its to 1. And so you could say a rule where if you have an edge that is XX, then that becomes XWX, something like that, for example. And then what would happen there is because and the way that it's found, for example, is these various variables that you're looking for, the only thing, they could be any number. The only thing is, anytime you have a repeat, they have to be the same. Right. So if our initial condition was this edge that was 1 1, then that satisfies the XX, right? Because 1 is the same as 1. So you found the thing that the rule applies to, and then you just apply that rule to it. So you have. it's pretty.
George is laughing because he's seeing my face as my mind is blowing up, which I hope it is at your end as well.
So yeah, essentially you have states of hyperedges. You find the hyperedges which some rule is applicable to, and it will be denoted by just saying, okay, you have, like you find 3 values in a hyperedge, and 2 of them are the same, or something like that. And then it turns into something else. And sometimes this can create new vertices, right? So you might have, XX becomes XWX. So our system of one edge connected to itself via vertice 1 would become that same vertice but connected to another. So you sort of have a hyperedge connecting all 3 or 2. Sorry.
So if I get this right, you're basically saying that, and you have to. I'm going to row quite considerably far back to the beginning here. What you're saying is that the emergent properties we see in the universe are potentially caused by a process similar to what you're talking about, and most of the time we try and describe the universe using maths, and like the maths is things where we talk about things like string theory and stuff like that.
Yeah.
And we're just basically hammering away at the universe using maths. Whereas Wolfram is proposing, instead of using maths, we use these kind of computational like almost like little algorithms at the beginning to sort of show the emergent properties of the universe. Is that right?
Yeah, I mean, I guess the big idea in sort of the last, like maybe 200 years was, or probably closer to 400 in science was we should look at like various phenomena in the world and then try to model them using maths.
Yeah.
But I guess this new idea, and this is why he wrote a book called, a new type of science.
Yeah.
Or a new kind, something like that.
Yeah, it's quite poo-pooed, this book, though. It's very controversial, his new kind of science book.
Well, yeah, I mean, I guess that's the case with anything, is the longer something's been running, the less they're likely to adopt something new.
Yeah, no, that's true. But I think that he has a few problems, which a lot of people.
Oh yeah, I mean, definitely.
But there's some big heavyweights that seem to be on his side, like Hooft and all those kind of people, where they're sort of looking at these kind of systems to generate the rules of everything, kind of thing.
But yeah. So you have these rules and states. And like with all of these other cellular automata that we've been talking about, you can have systems which produce very complex shapes, as well as simple ones, obviously, because some rules just
or no shapes at all. Some of the rules just break down.
They just die
make
instantly.
nothing.
Yeah. If one of the rules was, if this, then nothing.
Yeah.
Then exactly. Nothing would happen. But like. What some of them produce shapes, but by the way, the idea is you'd have like these shapes, like one of the rules when applied to just a single vertice connect or vertex. Sorry, when it's singular, it's vertex. But a single vertex, when the rule is applied to a single vertex attached to itself 4 times, it produces a very, I mean, it's the shape that's always used in the thumbnails of videos and things about this, right? It's quite, it's usually the front cover, but that's after 14 generations, and that produces 6,000 vertices, right? So we've gone from 1 to 6,000 in 14 generations. But Wolfram says that our universe may be something like 10 to the 400 vertices.
Yeah. I like the fact that you were telling me earlier on about how the speed of light might be to do with the fact that you've got these discrete...
The fact that you've got a tick speed in the universe, because every time this hypergraph updates with these rules, that's 1 tick, right?
Yeah.
And it will be something like 10 to the 48 ticks per second. which is a lot of ticks. But when you're going so fast, that actually does matter, and it means that there is a limited speed to how energy could go. But this model implies so many things, as in it's not added in. It just leads you to the conclusions of like general relativity, special relativity, quantum mechanics.
Well, that's the thing. I think quantum physics, you see, is itself via Bell's theorem, which is very well known and very well kind of, this is like hyper accepted. Bell's theorem is that quantum physics and hidden variable theories are incompatible, right? You can't have this local hidden variables theory. And this doesn't it sound like a local hidden variables thing? You've got these like the structure of the universe is being caused by.
But they're not local.
I know. See,
they're fundamental.
Oh, okay. See, this is the bit that blows my mind. I don't know anywhere near enough to get down into the. But
here's another thing. It's also kind of has in it its model black holes as well, because you can think of black holes as like the event horizon being a wall that stops any information from traveling. It's sort of like a pocket universe in a way, where it has the same laws as our universe, comes from our universe, but there's no bridge towards them. Right? They're just separate in terms of it's literally black, right? You can't see anything in it, and there are certain rule sets and initial conditions in this automata that Stephen has been found, which actually leads to like branches completely going off the main group. So there will be vertices which aren't connected in any way, in any route to other vertices.
Now, could it be we have a genius in Stephen Wolfram who, like maybe string theorists, have accidentally gone down completely the wrong path?
But like you kind of have to try, right?
Yeah, no, I'm not having a go at them. But I mean, it's
what if?
Yeah, because it's amazing. I mean,
if you find a cellular automata, or just an automata generally, because I guess this isn't even cellular. There's no geometry.
Yeah.
If you find an automata which perfectly describes our universe, even if it's not actually what's happening,
it's got to be useful.
It's still. If something perfectly describes, if a process perfectly describes the way that everything, then like how different is it to being true?
Oh man, yeah, I think, this is one of those things, isn't it, where it seems like a really great idea and seems to have a real insight, but has cellular automata been actually useful in anything other than a pseudo random number generator or
well, it's used in modeling physics. For example, there's a cellular automata which models fluid simulation, for example.
Yeah, and that's been reasonably successful, hasn't it?
Well, yeah, it's used in video games, in movies and things. There are other alternatives, of course, but it's nice to know that it's achieved something.
Yeah, that something's come out of it. Yeah, I mean, I guess so. I mean,
but I guess it never really was a practical thing. It's more like a lot of it's used for analogy, and the other. It could literally be like the entire universe is one instead of it being a practical thing.
I'm going to finish. The thing that was blowing my mind was the fact that the humans themselves. Our society kind of acts like this kind of emergent property as well. That like you think humans are running a simple set of rules, and then it all comes together, and maybe society is like a rule 120 of a human automata, and it's just like that. That's what's frightening. But I really liked as well, because you sort of sent me down this path. I found this guy called Adam Block, who's an astrophotographer, and he'd written a code that basically using cellular automata and kind of based on John Conway's Game of Life, he managed to recreate a spiral galaxy in code, so that the spiral arms were being formed because of the way that these
neighbors.
these simple rules, and he managed to find a way of just generating these things. So I'll put a link to that because it's really, really cool.
Yeah,
The
another
Galaxy
thing-
simulation via sort of Game of Life seems to be hints that they're onto something a little bit, right?
I mean, oh, definitely, yeah. And but if people are wondering, like, how does space or like dimensions come out of a dimensionless structure? And I think it's sort of hard to like think of, but essentially, at least you know, from the limited amount that I've read on this, you can define the number of dimensions as you well, first you've got to generalize like some sort of equation for the number of dimensions in any given space. So in our own, if you had a grid in 3D and you start at any point, it's completely arbitrary, and you go out.
So it's like a grid, but it's a box of grids. So
it's like
lots
a box.
of strings and wires going across. Yes.
Imagine like just a like a 3D chessboard.
Yeah,
you know?
like I guess like Lego, like a big massive Lego block. Yeah.
Just like a grid, a 3D grid.
Yeah.
Just a 3D grid.
Just a 3D. Yeah, a lattice.
That's
There we
the
go.
word.
There
That's
we go.
the
A
word.
lattice. There we go.
Lattice. So you have a lattice, and you take any points, and you from that point you branch outwards, right? Mm-hmm. And you basically look at how many new vertices have you selected from branching out one joining one edge, right? So you keep going across these edges one step at a time, and you measure how many more or how many new vertices you've gone to, you can select from that distance. And in our own universe, that's inverse square, right? Because at least it averages to that, it approaches the inverse square.
Yeah.
Because eventually, what you end up having is something. If you go for like 1 million steps,
Yeah, you end up with a sphere,
basically a sphere. Yeah.
which is pi r squared, and that's where you
No,
get your
okay,
inverse.
4/3 pi cubed.
Yeah. Oh, 4/3 pi. No, but it's the surface area, isn't it? If it's inverse square.
Oh yeah. Sorry, yeah. The surface. So you measure the surface. Either way, you can you can use the area or you can use the
Volume.
the volume, the area or the volume. Yeah, surface area or volume. Either way, you get the same. You come to the same conclusion. But and you look at 2D, for example, and it's a similar thing. And with this, you can kind of generalize what different dimensions lead to what different ratios of this dimension, right? So, and with the game with this cellular automata, because you have these vertices connected with edges and hyper edges and things, you can count the you can take any point and measure the average sort of gain in vertices as you step out from that. And with that, you can have this generalized view of dimensions and measure how many dimensions that universe will have.
It's blown my mind. Anything else to add to cellular automata? That it's fun, isn't it? It's a fun thing, but it's just like one of those. It's one of those branches of science. You think, is it a dead end, or is it? Or
There's only one way to find out.
There's only one way to find out, and that's go down it. I guess it's the you often see this moaning that perhaps science is a little bit too conservative sometimes, and maybe that there's too many people hanging on to the things that they kind of love, and it takes someone like Wolfram or someone like Weinstein or one of these other crazy people who seem to be banging on about a theory of everything. To kind of upturn it, but let's see who does it. I mean, we're kind of waiting for a breakthrough, aren't we?
Yeah.
But we need the next Einstein, really.
Yeah.
Because that's kind of where we're waiting, isn't it?
I do need to give a shout out to Bert Chang as well. I believe that's his name. He made a continuous cellular automata that actually gives he's studying the biology of a universe he created, essentially. Like, I mean, they're literally living beings he's discovered in his own cellular automata.
Oh my god!
Right, it's a continuous one. But
basically, he's lost in his own world.
Yeah,
this guy.
there are creatures in these automata which can self-repair and self-replicate and move across, and react to stimulus.
Wouldn't it be weird if some of them have become self-aware in the program?
I don't think they're quite that complex. I mean, they are just
Who knows? what is consciousness, George? Let's go down that route, or let's not, because we're going to have to wrap this up.
The consciousness thing of the Wolfram model it gets pretty crazy. I recommend you go onto Wolfram's blog and look at that, because it's just
where he actually models consciousness in it as well.
Oh yeah, it models
you're
everything.
Joking.
No. Look, because here's the thing I forgot to mention is you may have been thinking, well, what if this rule applies to multiple sets of edges, of hyper edges?
That's definitely what I was thinking. It's what you were thinking, wasn't it, listener?
Yeah, it is definitely what they were thinking. They're thinking, hold on, George, when you've explained this to me, you didn't take into account the fact that it could apply to multiple sets of hyper edges. Well, if it does, that there is this weird thing about consciousness and how the updating order kind of doesn't matter.
Oh no.
I mean, I really, it's like really,
well, yes,
it gets so hard when it's sort of in this consciousness stuff. And I just recommend you look into it yourself, because it's really, it gets crazy. But no, it's a really good one to look at, the Wolfram model, even for fun, you know.
Do you know we were talking about No Billy Crater? There's actually a No Billy Cellular Automata as well. I don't think it's related though.
Probably not.
No. Right. Unless it is. Oh no. This other Nobili is spelt with an I at the end rather than an E. Right. George, if people are interested in the Interplanetary Podcast and our crazy musings for the day, where should they go?
Well, before that, we have to mention the number of this podcast.
Oh, yes.
256. That's 2 to the power 2 to the power 2 to the power 2.
Yeah, it's an 8-bit podcast,
yeah,
as they say.
It's the max value you can store in 8-bit.
Yeah, 256. It's actually... 256 is the bit rate that I actually do this podcast at as well when I'm converting to MP3.
It's meta.
It is meta, isn't it? So I won't get confused when I convert it this time, because I sometimes get confused. I sometimes put the episode number in when I'm supposed to be putting the 256 in. But this time, better put it both. Well spotted. It's an 8-bit podcast. Right. Right, that's it. So, yes, where should they go to if they're interested in 8-bit podcasts?
They should probably go to www.interplanetary.org.uk.
That's exactly right. And if they're super into it, you should go to patreon.com
/Interplanetary.
Oh, nice. Good work. And absolutely massive shout out to all the Patreons out there. Thanks very much for supporting the show. Without it, it would be absolutely awful. Hopefully we've got some good interviews coming up over the next few weeks.
Yeah.
And actually there's ESA Open Day, which I'm going to be involved with. So hopefully there'll be some awesome content coming out of that as well. So I look forward to that. We'll see how that all pans out. So see you next time, Spacecraft!